Anyway, any questions at all? I thought it was 24, but maybe a lot didn't, they dropped or anything. Go ahead. Did you have a question? Nothing? Did you all do it? You done the homework? And you're all good with it? All right. Move on, man. Now we're to oblique incidents in the book. This is on page, starts on page 359. Now, the thing about this is oblique incidents, when the angle of incidence becomes 90 degrees, it is just the normal reflection coefficient and transmission coefficients we've been dealing with, all right? But in general, here's the way it's done in Dr. Wentworth's book. Which these markers were a little darker. So what they're going to do is, the coordinate system is going to be Z here, and this is going to be X. And then we're going to have an electric field, a plane wave incident here. And it's going to be at some angle theta incident. And the electric field, though, is polarized out of the board. So the electric field itself is out of the board. Can you all imagine that, class? In other words, this is called TE polarization, transverse electric polarization. Here's why it's called that. If you look at the electric field, this is the interface between region 1 and 2, called this region 1 and region 2. And this is some other material, doesn't matter what it is. But if you take a look at this, the electric field is actually perpendicular to the plane it's traveling in. Can you all imagine that? The electric field is on the board, so it's like this, it's propagating in this direction. The H field has to be perpendicular to both the direction of propagation and the actual E field. And E crossed H is always the direction of propagation. Y'all follow me on this, guys? Everybody? So, E crossed H is direction of propagation. If you have a right hand, you put your index finger in the direction of the E field, then you rotate it over the short angle, or like turn the handle on the door into the actual H field, your thumb points in the direction of propagation. When this hits here, there's going to be also a wave that's transmitted. It will have an electric field that's perpendicular. By the way, this is sometimes called parallel polarization. And I see the problem is, I don't want to confuse you, but if you see this electric field like this, you see how it's actually in the plane of the surface? It's parallel to it. Can you imagine that? This is the surface, right? Here's region 1, here's 2. This is an infinite planar surface. So it's like this electric field is completely in the plane, completely in the surface it interfaces. It's transverse to the actual plane it's traveling in, which is the board, but it's actually parallel to the actual interface. It's completely aligned with it. You all see this? Everybody follow me? Now, contrast to this, if it was TM, transverse magnetic, then the magnetic field would be out this way, and the electric field itself would be in the plane of the board, all right? It would be like this, and that's called TM, transverse magnetic polarization. Can y'all follow me? All right, just hang on, you'll get there. So this is the electric field incidence. There's an electric field that's transmitted. It's like some of this electric field is going to be transmitted. It's going to have an angle here called theta transmitted. And the magnetic field transmitted would be as such. I'll get the equations in a second. This is going to be the transmitted electric field. And some of it's going to be reflected in this way. And this would be the angle of reflection. And the electric field would still be out of the board. But the magnetic field, if you look at this, E cross H is the direction of propagation. So E cross H would be the direction of propagation. And here, it would be in this direction. So I'm just giving you, trying to just give you an idea of what's going on. Now we'll get to the mathematical description. For the incident electric field, this is a plane wave again. These are plane waves. And this is for TE polarization, but it's plane waves. The incident electric field is expressed as this. It's E, or some E naught incident, just as before, e to the minus j, and we're assuming this is losses, by the way. Losses e to the minus j beta 1, and then it's going to have x times the sine of theta incident plus z cosine of theta incident. I'll explain that in a second. And it's going to be perpendicular to the board, so it's in the AY direction. That's the incident electric field. This is the angle of incidence here. There's going to be an actual reflected electric field. It's going to have some E naught reflected, e to the minus j beta 1. And it will have an x times the sine of theta incident, or theta reflected. But it will be minus z cosine of theta reflected. And I'll get to the reason for that in a second. And then there's going to be some transmitted electric field. And that's going to be some E naught transmitted, e to the minus j. Here it's going to be beta 2. It's going to have the same form as that one, except the angle is going to change. It's going to be x times the actual sine of theta transmitted plus z cosine of theta transmitted in the AY direction. Now, I've got to spend a few minutes explaining some of this stuff here. This is in the book. And it looks like it's messy for starters. There's a lot going on. But it all boils down to something pretty easy to say. You take a look at this right here. The first thing you have to understand is why it's this way. Well, what we actually have is, if you look at this, we have something that's coming in, and what they do in the book, I think he calls it Z hat, but I gotta just check for a second. Try to do it this way. So, if this is the x coordinate, x distance, and this is this is the z distance, and this is the x distance, and this is the angle of incidence. See, you have the angle of incidence here, alternate interior angles. This would be the angle of incidence. And we're talking about, if we actually are talking about something z hat, this is going to be actually the direction that it's propagating. I'm trying to do this in the easiest way to understand. It's propagating like this. Can you all see that? That's the direction of propagation, right? So if you look at this, that means the component in this direction, in the actual z direction, would be z times the cosine of theta incidence. And this would be in the x direction. And the x coordinate of this z hat would be equal to z times the sine of theta incident ax. This would be az down here, and this would be ax. So z hat itself has a projection in both x and z. This is going to bother you a little bit. Just imagine this. See, this wave's propagating this way. We have to express this distance in some way, just like we did, beta z before, right? All right, it has both an x and a z component. Follow me as it's propagating. You increment time, it's going to propagate this way. The z component would be this z hat times cosine. The x component would be z hat times, the sine of that. And a unit vector in the direction of propagation here, this is important. This unit vector in the direction of propagation for the incident field, it would be equal to cosine of theta incidence a z plus sine of theta incidence a x. This will bother you a little at first, but you're gonna see that it makes perfect sense. If you take a look at that, unit vector, this is a unit vector in the direction of propagation here. If you take a look at, I'll put the sign first. The sine of theta incident AX plus cosine theta incident AZ. Now just look at this. If it's coming in normally incident, in other words, if it's hitting the plane perpendicular, the angle theta incident would be 0. Do you agree with that? Can anybody imagine this? If it's coming straight in, this angle here goes to 0, right? If it's 0, if theta incident is equal to 0, the unit vector in the direction of propagation would be, well, the sine of 0, 0 would just be AZ. That checks that box. Makes sense, doesn't it? All right. Now, do the opposite. What if this angle is approaching 90 degrees? Well, then it would be going in the X direction. Do you all see this? So this works, all right? It will work. It'll bother you a little. I know it did me when I was going through this the first time. I was sitting where you were in college. But it works. A lot of times what you're going to see in books is they'll express this right there as some Z hat or some alternative. It's neither X nor Z in terms of its actual positional vector. It's a combination of both. You all follow me? Because it's not flowing in either the Z or X. It's flowing in a combination to it, an angle. So, back to this. Now we're going to get unit vectors. This is going to be the unit vector in the direction of propagation for the incident wave, and I just put that down there. That's equal to sine theta incident AX plus cosine theta incident AZ. Does everybody follow me on that? That's a unit vector in the direction of propagation for the incident wave. When you take a look at a unit vector in the direction of propagation for the reflected wave, now, take a look at this. Here's the reflected wave, right? We want a unit vector in that direction. Well, it's going to be the same as this in a sense, except now with Z, it's going to be negative. Y'all see this? Y'all follow me on that, class? But the X component will still be positive. So it will be the sine of theta reflected AX, but it will be minus cosine theta reflected AZ. It's got to be negative AZ. It's propagating the negative Z direction when it's reflected. Follow me, everyone? All right, keep going on that. What about the transmitted unit vector in the direction of transmission? Well, that's basically this form, right? They're both positive, but instead of the incident angle, now you have the transmitted angle. So now this one is going to be equal to the sine of theta transmitted AX plus cosine of theta transmitted AZ. What I'm going to do to make my life a little easier and yours too is I'm going to use the shorthand notation method writing some of this stuff. So I'm going to say that Z hat here is going to be equal to just X times the sine of theta incident plus Z times cosine of theta incident. Now, you'll see why I'm doing that in a second. So now, come over here. Now we're going to get the H field. Y'all follow me? I've defined the E fields in terms of mathematical statements that are clear and they're exact for propagating waves. Now when we talk about the H field, well, the H field, since it is a plane wave, can be gotten by taking 1 over eta in region 1, unit vector in the direction of propagation of the incident wave crossed into the E field, right? You know what I'm doing here? That's the shortcut method, right? For both E and H, we can do these little cross product things and get it. So now I can say that H incident is equal to 1 over eta 1, unit vector in the direction of propagation, which is equal to simply the sine of theta incident AX plus cosine of theta incident AZ. And it's crossed into the E field. The incident E field is E naught incident. Then just, I'll put E to the minus J beta 1 and just Z hat. I won't have to write that expression in the AY direction. Go ahead and take a look at that. I put the unit vector down. I have eta 1 because we're in region 1. And then I just use Z hat instead of writing that again. Y'all follow me? Now, when you do this, we gotta do the cross product, so what do we get? For the incident field, we're gonna have E naught incident over A to 1, that can come out in front. That's just a scalar value. Now, the next thing I have, we're gonna have two terms. I have AX crossed AY, which is, see this, AX crossed AY is, X crossed Y is Z, AZ, right? So I'm gonna have sine of theta incident, and it's gonna be AZ. All right? I'll put that e to the minus j beta stuff in a second. Now, what happens when I have AZ crossed AY? Z crossed Y is negative AX, right? Minus cosine theta incident AX, and it's still all times e to the minus j beta 1 Z hat. And that's an expression for the H field incident. Now, I want you to see how it makes perfect sense. E field incident is out of the board, it's propagating this way. Can you all see how the H field has a negative X component and a positive Z? Can you all see that right here? There's the H field. Positive Z, right? Negative X. Follow me? It checks the box. That's right. That's it. That's the actual incident H field in terms of the incident E field beta 1 and these angles, the propagation. So that's the incident H field. Now, I'll just tell you this. If we go ahead and write the reflected H field, I always run out of board space when I do this, but I'll try it right here. There are no erasers in here. Okay. First, if I take a look for the transmitted field, a unit vector in the direction of transmission is right there. I'll just leave that there. I'll just point to that. So we can say H transmitted would be equal to 1 over, now it's A to 2, we're in the second region. Unit vector in the direction of transmission is right there. That's equal to sine theta transmitted AX plus cosine of theta transmitted AZ. And that's crossed into the E field, which is E naught transmitted, right? E to the minus j, and here's going to be beta 2, and then it's going to have that expression x times the sine of theta transmitted plus z times cosine of theta transmitted, and it would be in the AY direction. This is a little, I've got it shoved into that corner, but y'all follow me that what I'm doing now is I'm talking about this term would be in the exponential. Can y'all follow me on this, class? This is spelled out in the book. If you have your book, you can look there. And by the way, this is the kind of stuff you have to at least have an appreciation for, right, how it's done. Because the problems that come after this are related to your understanding of how it's developed. It really has to do with how it's developed. So that's the transmitted H field. I didn't do the cross product. Can you all see that what I'm about to do there? It parallels this, except now the angle is transmitted, not incident, and also the unit vector is not the incident unit vector, it's the transmitted unit vector, right? Everybody follow? So if you do the cross product, you basically get this. You're going to get the transmitted H field here is going to be equal to some E naught transmitted over A to 2 in magnitude. And then I take AX cross AY as AZ, so I get the sine of theta transmitted AZ, and it's going to be minus cosine of theta transmitted AX, because I got Z crossed into Y, which is minus AX. And then I'll have that exponential e to the minus j beta 2 x, and then it's going to be times the sine of theta transmitted plus z times cosine of theta transmitted. And that's my transmitted H field. Can you all appreciate that? This might be a little tedious, but you have to at least appreciate why we're doing this. We're doing it based on what was already the groundwork laid before, where we can say that this is how we get the H field if we have the E field. We have to have the unit vector in the direction of propagation, we can do it. Now for the reflected H field, so that's incident, that's transmitted. For the reflected H field, here, that's going to be 1 over A of 1, down in the region A of 1. Unit vector in the direction of propagation for the reflected field is this. So it's going to be sine of theta reflected AX minus cosine of theta reflected AZ. And then it's crossed into the E field, which is E naught reflected times E to the minus J beta 1, and here it's going to be X times the sine of theta reflected minus Z times cosine of theta reflected, because it's propagating in the opposite direction, A1. And again, the only thing I'm doing there is rewriting what I have here in terms of the definition right here. But basically 1 over eta, unit vector in the direction of propagation cross E. I've just expanded that there. Follow me, everyone? All right, when you do the crossing on this, there's one difference, and I'll put it right here. H reflected, I can take the E naught reflected over A to 1. And then I have AX cross A1, which is AZ, so I get the sine of theta reflected AZ, but then I have AZ cross AY, follow me on this? AZ cross AY, which is minus AX, but there's a minus sign, makes this positive. So it's plus cosine of theta reflected AX, and then it's all times E to the minus J beta in the region 1 times X sine of theta reflected minus Z times cosine of theta reflected. And lo and behold, that's the reflected H field. So now I've got I've got the transmitted, reflected, and incident H field. I've got the transmitted, reflected, and incident E field for this problem where I have oblique incidence, I have a wave coming in, but it's not hitting this slab, this interface between region 1 and normal. It's coming in at some angle. And now I can go ahead and find out what the transmission coefficient and reflection coefficient are for this problem by using the boundary conditions. Now I'm going to have to do one thing to give myself a little more space. I'm going to do it right here. I'm going to try to do it right here. So whenever you have an interface between two materials, right? When we're talking about electromagnetic properties, if there's no surface currents, there's two things that we have to know. You remember what they are? What is the two things that you always know are true for static or dynamic electric fields? That the tangent electric field on one side is equal to the tangent electric field on the other. That's E tan 1 is E tan 2, right? And the tangent H field is equal, on one side is equal to the tangent H tan 1 is H tan 2, E tan 1 is E tan 2. Do y'all remember that? Now those are so important to really have an appreciation for. So when we come here, when we talk about E tangent in region 1 is equal to E tangent in region 2, well, what does tangent mean to you? If you have this wall as my surface, and I'm talking about what's tangent, if an electric field's propagating like this and it hits, you see the entire thing is tangent, the entire electric field. Y'all follow me? It's in the surface plane when it hits. If I had an electric field like this propagating this way, when it hit, only a projection of that electric field would be actually tangent. Follow me on this? Not the entire field. So when we look at this, E tan 1 is E tan 2, when we have TE or transverse electric or perpendicular polarization, well, I don't want to confuse you. Just leave this TE, transverse electric. That means the electric field is perpendicular to the plane it's traveling in. Follow me? When it hits, the entire electric field on one side is parallel, or in the plane, right, is tangent to the entire electric field on the other side. Do y'all follow me on this? Now, right here is Z equals 0, up and down that axis, right? You can let X equal 0 too, and what you get is the electric field on the first side would be equal to simply E naught incident plus E naught reflected, and the electric field on the other side is just E naught transmit. That's easy. Y'all follow me? Just take a look at this. Here's the electric field here. The incident field, it hits, some's reflected, both are in the same direction, both are parallel to this interface. is equal to transmitted electric field. And then when I do Z equals 0, X equals 0, I'm right here, right? Has to be true everywhere in that boundary, and I get this. Do y'all follow me? Now I can expand that one. That's just at the boundary, but I can also say that would be E naught if we talk about Z equals 0, because an important thing happens there. I could say it's E naught incident, but it'd be E to the minus J beta 1, then it would be X times the sine of theta incident plus E naught reflected times E to the minus J beta 1 times the sine of theta reflected, and that would be equal to E naught transmitted times E to the minus J beta 2 times the sine of theta transmitted times, I should have put an X here, times X. See, when Z goes to 0, what happens is this Z cosine theta reflected goes away, and the Z cosine theta incident, Z cosine theta incident and Z cosine theta transmitted go away in those equations. So I'm left with this. Now this is real important right here to see this. That's all along that interface. Z equals 0 is where the interface is. It's up and down here, right? That's Z equals 0. Does anybody know what comes next? There's a very important law we get from this. It's called Snell's law. Do you remember Snell's law of reflection? How many have heard that in physics? All right. In Snell's law, what happens? Snell's law gives us, if I have electromagnetic waves, light, anything, incident from one region to the other, and I know the angle of incidence, I know the angle of transmission. Do y'all remember that? All right, here's how it happens. If I look here, I'm going to just try to explain this thing as easy as I can. You see how for this to hold true, the only way for this to hold true for all values of X would be for that argument, and that argument to be the same. Y'all follow me on that? If they weren't, suppose this coefficient of X is different than this coefficient of X here. Just follow me on this, all right? Well, then if I change the value of X, I'll get a different complex number, and it would only be equal at one point for X. All right, so this is how Snell's laws come about. It says that beta 1 X times the sine of theta incident, it must be equal to beta 1 X times the sine of theta reflected, and it must be equal to beta 2 times X times the sine of theta transmitted. That has to equal that, has to equal that. I omitted the J's because they just complicate things and they just cancel. Now when you look at this, I'm going to also, can you all see I can get rid of X in that statement? It appears everywhere. You all see it? So I'm going to get rid of X. Now look at this. It says beta 1 sine of theta incidence is equal to beta 1 sine of theta reflected. What does that tell you about the reflected angle and the incident angle? They're the same. Do y'all follow me? How many know that from playing pool or something? That the angle of incidence, if we're talking about non-English and all that, if you hit, right, it bounces off at the same angle. In other words, the angle of incidence is the angle of reflection. We get that from here. So theta incidence is equal to theta reflected. Eureka. We get one other thing. You get beta 1 times the sine of theta incidence is beta 2 times the sine of theta transmitted. And what that is Snell's law. I'll put it here. And let me give you an example of this being in use. So when we talk about Snell's law, you've heard this, right? You get this in high school physics usually, right? How many of you remember Snell's law? You're kidding me. No way. Come on. You went through high school, right? Remember F equal ma in physics? Snell's law was fundamental, right? It was the bending of light. For Snell's law, it's really beta 1 times the sine of theta incident is equal to beta 2 times the sine of theta transmitted. That's the formal way to do it. Now, Usually we can do this, we'll assume no loss, so we'll assume lossless region. This will hold with a lossless region. What is beta for a lossless region? I don't know if you're doing this to spite me or what. What is beta for a lossless region? Lossless, come on, man. What is it? It's omega, right, times square root of mu epsilon, right? This would be mu1 epsilon. You all remember that? That's beta 1 times the sine of theta incident is equal to beta 2, which would be omega times square root of mu2 epsilon 2 sine of theta transmitted. Follow me? Now, y'all see how omega cancels. Frequency is always the same, never changes. So the omega cancels, and I get this. This is Snell's law. Usually what you see for Snell's law is they'll go a step further and they'll say it's non-magnetic. Or if it's non-magnetic, that means mu's on both sides are the same. So now I get the square root of epsilon 1 times the sine of theta incident is equal to the square root of epsilon 2 times the sine of theta transmitted. And because epsilon 1 and epsilon 2 are just epsilon relative 1 epsilon naught, epsilon relative 2 epsilon naught, we can get rid of the epsilon naughts, so we're left with the square root of epsilon relative 1 times the sine of theta incident is equal to the square root of epsilon relative 2 times the sine of theta transmitted. Do you agree with me? Now, do you remember what the square root of epsilon relative was? There's a term used. In physics, I know that the guy probably beat it into you. It was called the index of refraction. Do y'all remember that? Index of refraction? And usually the index of refraction is given the symbol small n. Unfortunately, my etas look like n's. But this is actually equal to the index of refraction in region 1 times the sine of theta incident is equal to the index of refraction in region 2 times the sine of theta transmitted. Now that's Snell's law the way the physicists write it, where eta, or n there, is the index of refraction square root of epsilon relative. We're going to do a little problem here. With me? Believe me, I'm coming back to this. I got a lot to say. And oblique incidence is probably the one thing that, of this chapter, it is the thing that's a little more confusing. Right? So I'm just telling you, there's a lot going on. I mean, the mathematics get complicated quickly. So when we take a look at this, the best thing to do when I talk about Snell's law is give you an example right now. Best example I can think of is water. So we're going to take a look at H2O, water. And H2O has the general way to do it, we'll assume it's a lower frequency, is epsilon relative is about equal to 81 for water. And we'll assume it's air up here. And air has an epsilon relative of about 1. Y'all with me? All right, now, if I have a ray of light, or I'm shining light down at an angle right here, incident angle, so got light coming down this way, and E field's polarized out of the board, and I want to know what angle it's going to bend down here. So now I want to know the transmitted angle. Y'all with me on this? So what I'm going to do is I'm going to say this angle, light's coming in, I'm going to say the incident angle is 45 degrees. And I want to see what the angle of transmission is right here. Y'all with me? Now, has anybody ever shot a bow and arrow into the water to try to, shoot a fish or something? Anybody? Man, just not the usual bunch. I usually have a few kids that's done this. Well, you always shoot under the fish. I don't know if you've ever heard of that. All right, the arrow bends because of the optical bending of light under. What happens is when we take a look at this, I'm going to take a look at this equation, that one right there. So I have the square root of epsilon relative 1 times the sine of theta incident is equal to the square root of epsilon relative 2 times the sine of theta transient. Okay, follow me. Epsilon relative 1 was 81, by definition. This is region 1, air. This is region 2. The angle of transmission is in region 2. Do y'all follow me? And it's always measured with respect to the normal. So square root of 81 is? 9. Okay, finally. Finally got it. Now we got times the sine, right, of 45 degrees. What's the sine of 45 degrees?
1 over square root.
1 over square root. Better. Yes, square root 2, right? All right, that's equal to what? Hold it. I did this backwards. This is all me. Epsilon relative 1 is 1, right? Square root of that is 1. But sine of 45 degrees is square root of 2, mind that, is equal to epsilon relative 2. Square root of epsilon relative 2 is 9, right? Square root of 81. That's 9 times the sine of theta transient. Anybody got a calculator here? So the sine of theta transmitted is 1/9 square root of 2, or theta transmitted is equal to a sine, the inverse sine of 1 over 9 square root of 2. All right, what is that in degrees, anybody? I know you got calculators because it's good as that too. It's going to be small.
It's real small.
Oh.
1.37 times 10 to the minus 3.
That may not be right. That may, I think you did this. This is, when you're doing this, you gave me radians, I think, didn't you? Go ahead and do this. Inverse sine of 1 over 9 square root of 2.
Inverse, that's right.
A sine or sine to the minus 1.
4.5.
What?
4.5.
That sounds better. 4.5 degrees. Now, what does that mean? So if I'm looking in the water and I have a flashlight coming at 45 degrees, the light actually bends almost straight down. It's only got 4.5 degrees off the vertical axis, right off the perpendicular. And vice versa, if light's coming from here, from water, it's bending this way. Y'all follow me? Now, the optical illusion is that there's a fish under here, and I see a fish, I think it's in this direction, all right? So if I aim right there, I'm gonna shoot way over the top. The fish is down there. Follow me on this? So that's the story, you always shoot under the fish kind of deal. But when you have anything in water, and you're looking at water, the light rays always bend towards the actual perpendicular. It goes from the less dense to the more dense with more bend. So this, you can see, it's kind of like, you can look at light and it's bending like this. In the limit, as the value of epsilon relative goes to infinity in the second region, it goes straight down. All right. If you take a look at the limit there. All right, that's Snell's law. Very important law. But we're going to keep going. We're going to get the reflection coefficients and transmission coefficients for these regions. And I'm going to do it here. Now, I've written down all this stuff, and if you have your books, you can look there. I encourage you to bring your books. Just because you can mark them up, and you book something you don't usually lose. If you lose your notes, they'll be ripped up or something. And always make sure that, I tell this to all the students in engineering. You know, when I was where you were, I took a lot of courses. I didn't take sociology. I didn't care about keeping sociology. Look, I sold it back. But everything in engineering, in math, in physics, and chemistry, keep those books. You're going to use them for the rest of your life as reference material. Even though the stuff's on the internet, when you ink up your own book, you know, back in the back of your mind, where you made notations about certain things, like Snell's law, like we're going to see Brewster's angle, and you can go back and look, and then, oh, there it is. Right. I've learned this about the internet, and I learned it especially because physics and engineering use different units at times. Physics likes to use the English system. They like to use different notations for Maxwell's equations. We use the MKS system, right? All the time. We don't use the velocity of light in feet per second. It's in meters per second. We don't have weight or what is it, slug, or mass would be in slugs, isn't it right? Forces in pounds. We'd use what, newtons, right, and kilograms, right? And the nice thing about MKS, it's seamless in terms of the actual relationships across any type of, if you go from thermodynamics to electromagnetics, there's no problem. There's no unit conversion and all this stuff. Have you had thermo yet, anybody? Oh goodness, you're in for fun. Because the units will drive you nuts. They haven't adapted. Yeah, you get steam tables. I'm just telling you, I know. I had to do this. Okay, so back to this thing. Now we're going to get the actual transmission and reflection coefficients. Remember, I put down E tan 1 here was equal to E tan 2, right? And that means E naught incident plus E naught reflected is equal to E naught transmitted. I wrote the general form for that at the surface, at the interface, and then we got Snell's law from it. But this is at x equals 0, 2, and that's still true. Now, when we look at H tan 1 equal to H tan 2, all right, here's where it's a little different. I erased my drawing here, but I can recreate it fairly quickly. I know I had an incident electric field coming out of the board, but I had a magnetic field that was in the plane of the board. Do y'all follow me? Now, if you take a look at this, the magnetic field is parallel to this surface. If this is region 1 and this is region 2 right here, that would be the x component of the magnetic field. Can you all see that? The z component's in that direction. This is the z-axis. This would be the x-axis. So I want the x component of the magnetic field of the incident and reflected magnetic field equal to the x component of the transmitted magnetic field. Can you all see this in your mind? All right. I'll tell you where it is in the book, because I run out of board space quickly. Does it? Oh, it's on page 364. So, when I go ahead for this one, and I do the math on, I'll do it here. This is H tan in region 1 equals H tan in region 2. Now I'm going to get E naught incident over A to 1, and it's going to be minus cosine of theta incident here. It's going to have the exponential terms and all that, but that doesn't matter. This is the x component, AX. Then it's going to have plus E naught reflected over A to 1 times cosine of theta reflected, but that's a positive, is equal to E naught transmitted over A to 2, and then it's going to be times minus the cosine of theta transmitted. Now, I'm trying to do this in a way that this is shown in his book. And I got rid of the e to the j beta stuff because we can just assume x is 0, get rid of all that. But this is at the interface. Now, when you take a look at this right here, I got incident, reflected, and transmitted. The first thing you can do, you don't have to be able to recreate this exactly, but you have to be able to appreciate it. Since angle of incidence is angle of reflection, just put angle of incidence. Y'all follow me? We proved that, right? Angle of incidence is the angle of reflection, right, for a planar surface. Next thing we do is we realize that the transmitted electric field right there is equal to E incident plus E reflected. Can y'all see this? That's E transmitted is E naught incidence plus E naught reflected. That's from the boundary conditions. I can replace E transmitted there with E naught incident plus E naught reflected. Y'all follow me? Now, I'm going to try to do this in a way that doesn't cause you to go nuts. So now I have E naught incident over A to 1. I have minus cosine of theta incident plus E naught reflected over A to 1 times cosine of theta incident, because they're said, is equal to minus cosine of theta transmitted over A to 2, but now instead of putting down E naught transmitted, I'm going to replace it with E incident and E reflected. Can y'all follow me what I'm doing? All right. I know it doesn't look like fun, but just hang on. You're going to see this thing falls apart in a second. So I want to get something, and I want to get the reflection coefficient, which is the E naught reflected over E naught incident. Can y'all follow me? That's my goal here. I'm after that. So first thing I do is multiply everything through by A to 1. When I do that, I get rid of this. And I get A to 1 here. That's eta, right? Next, I multiply everything by A to 2. So I get A to 2 here, I get A to 2 here, and I get rid of this. Now I'm getting ready to do what I need to do. Now what I'm going to do, and you just appreciate what I'm doing. Y'all follow me? I'm trying to get just E naught incident, or E naught reflected over E naught incident, and then everything else on the other side. Now I go ahead and divide everything by E naught incident. So I get rid of this. And then this becomes E naught reflected over E naught incident, which is called the reflection coefficient. And it'd be the reflection coefficient for a TE wave. And then this right here becomes 1. And this becomes the reflection coefficient for a TE wave. Transverse electric. Y'all follow me? Now, what I'm going to do is gather the terms on one side of the equation, have actually the reflection coefficient, everything else on the other. Follow me? So when you do this, and for the sake of time, I'm going to come over here. I can see I've got to take this, right? Or well, basically, I'm going to take this term on this side, take this term on that side. And when I go ahead and mess around with it, you can check yourself on this. You get the reflection coefficient equal to A to 2 times cosine of theta incident right here. And it's going to be minus A to 1 times the cosine of theta transmitted over A to 2 cosine of theta incident plus A to 1 times the cosine of theta transmitted. And that is the reflection coefficient for a TE wave. And the reflection coefficient, by the way, is equal to the ratio of the reflected field over the incident field. That's what it's equal to. So that's the reflection coefficient. I want to show you something with this. You know, if you have a normally incident wave, right? A normally incident wave would have an angle of incidence of 0 degrees. Do you all agree with that? Remember, this is how the angle is measured from the normal between the surfaces, right? So if it's 0 degrees, it's normally incident. Do you agree with that? That's what we've been doing before. If it's normally incident, what does this decay to? Well, the cosine of theta incidence would be cosine of 0, which is 1, right? Cosine of 0 is 1. The transmitted angle would also be 0. From Snell's law, it's got to be 0. So that means I get 82 minus A to 1 over 82 plus A to 1. Look, do you all remember that? From the reflection coefficient for a normally incident wave. So when you go down and let that angle become 90 or become 0 degrees, in fact, you get the reflection coefficient you knew before. The transmission coefficient will be equal to, for a TE case, 1 plus the reflection coefficient, or that will be simply 2 times A to 2 cosine of theta incident over A to 2 times cosine of theta incident plus A to 1 times cosine of theta transmitted. And that's the transmission coefficient, which is equal to E naught transmitted over E naught incident. But this is all for TE, transverse electric. In Dr. Whitmer's book, he shows you this. He doesn't put it the way I do. He has E reflected on one side, and he has E naught incident times the reflection coefficient on the other. But this is on page 364, equation 133 and 134. Okay? So now I got transmission and reflection coefficient. And it seems like there's a whole lot of math that just is redundant, I have to do. This is what comes out in the long run. You can prove this to yourself. Good students usually take the time to try to recreate this proof on their own based on the actual formulas and stuff over there that we assume. And I gotta tell you this, you know, when you get, yeah.
In the book, it's got 8/2 cosine the angle of the transmission.
Where are you looking, sir?
134.
134? I don't have a page 130.
Not 134. Like it's on page 364. Equation 134.
This is
Look in the denominator.
That's 8/1 cosine theta transmit, 82 cosine theta incident. That's the same. I have them reversed. This one.
Okay, you're right.
All right, it's the same.
I was looking at it wrong.
I mean, I had the first part of that. All right, on where the.
I was looking at it wrong.
Yeah, but this is true, and I gotta say one thing. This is for transverse electric. It's not for transverse magnetic. That's completely different. We'll get that up. And I'm just gonna say this. This stuff right here, all the formalisms to get to this point, sometimes it just becomes a little overwhelming at 8 in the morning. Right, look through it, make sure you appreciate how I did this. But the key thing to take away is that's reflection, that's transmission coefficient for TE wave. So if you knew the incident electric field, you knew what the regions were, you knew the frequency and everything, then you could get the transmitted angle from Snell's law. Follow me? Use Snell's law to get the transmitted angle. Then you can get the value of the reflected and transmitted electric field for these. But you need the transmitted angle. You all see that right there? Have to have the transmitted angle to use this. And you get it from Snell's law. Okay. So now for TM polarization. This is the other part of it. By the way, for this stuff, you know, I didn't just warn you with a perfect memory or anything like this. The reason I know this stuff is because I've worked with it. All right, when you work with something, just know it. You know it backwards, forwards. I have to. And to be frank about it, the more you immerse yourself in problems and in understanding phenomena, doing problems is the best way in engineering, the more it becomes almost second nature to you. It's like riding a bike after a while. You can't help but know. So, next thing is TM polarization, transverse magnetic polarization. All right, we're still talking about plane waves. Here's region 2. Here's the normal. We'll call this the Z direction. This is the x-axis. Now it's transverse magnetic. Now we do everything we did before, but instead of putting the electric field perpendicular to the actual plane, it's transverse, and we put the magnetic field. So now we're going to do this. We're going to have a wave coming in at a certain angle of incidence. All right. But now the magnetic field itself is going to be out of the board. And so the magnetic field, the way Winthrop does this is he calls this magnetic field E naught incident over 8/1 is the actual magnetic field. And the electric field is going to be in this direction. I've got to make mention of this. Here, the magnetic field is in this direction. The electric field is in this direction. Remember, E cross H is the direction of propagation. It's that direction. It works. I'm going to write equations for this, but you have to see this. The electric field's in the plane of the board. Magnetic field's perpendicular. E cross H is that direction, that's the angle, that's the actual direction of propagation. Y'all follow me, class, on this? Same as before, you get a reflected field right here. And your magnetic field here is going to be perpendicular, but it's actually going to be into the board. And that magnetic field is E naught reflected over eta 1. And since that's into the board, the electric field is actually in this direction. That's reflected electric field. And likewise, this would be theta reflected, which is theta incident. You're also going to have a transmitted angle here, and here the electric field, or the H field, is out of the board. The H field, he likes to use E naught transmitted over eta 2 here, and the actual electric field is in this direction. E transmitted is in this direction. I'm going to write the equations for this, but I'm going to tell you, by this time you're probably kind of a little saturated with some of this stuff, but I'm just going to get them out there. They're in your book. Let me tell you where they're in your book, so you have them. This is TM polarizations on page 366. So here, the H field incident is going to be equal to E naught incident over eta 1. He doesn't like using H naught incident. He always puts the E field in terms, or the H field in terms of the E field and eta, right? Because it simplifies his life a little. Then this is going to be times E to the minus J beta 1 x times the sine of theta incident plus z times cosine of theta incident. And it's going to be in the A, in this case, A y direction. The actual reflected magnetic field is going to have minus E naught reflected over eta 1. It's going to be E to the minus J beta 1. It's going to be x sine of theta reflected, but you can put theta incident because of the same angle. But then it's going to be minus z times cosine of theta reflected, or theta incident. Might as well put it theta incident. And it's going to be a y, but it's negative. And finally, the transmitted H field will be equal to E naught transmitted over eta 2, e to the minus j beta 2 times x sine of theta transmitted plus z cosine of theta transmitted. And this is going to be in the AY direction. Just want to see one thing here. Yeah, he shows us, if you look at equation 6.139 on page 366, he shows a reflected magnetic field having a negative sign in front of the E naught reflected over eta. All right, those are, now that was like the E field from before. Now that's the magnetic fields we start with. They're all perpendicular. Now we can get the E field. And do you remember how to get the E field using that cross product, or the basic cross rule? It's what?
Negative.
Minus, right, eta, right? Unit vector and direction propagation crossed into H, right? Y'all remember that? All right, there's a minus sign here. Let me cut to the chase on this. When we do this, the unit vector and direction propagation for this one, right here, is going to be simply sine of theta incident A x plus cosine of theta incident AZ, just as before. All right, this seems a little much, just hang on. All right, I'm almost done. So when I come here, I'm going to get the incident E field. Incident E field will be equal to minus eta 1. This is going to be equal to the sine of theta incident AX plus cosine of theta incident AZ crossed into the magnetic field. And this is nice, it's just E naught incident over eta 1. The etas are going to disintegrate in a second. Crossing this is e to the minus j beta 1 times x sine of theta incident plus z cosine of theta incident. And it's a y direction. Now, I want to write this down one time, at least for the incident field, so you see it. when you take a look at this, what's the first thing you notice? The eta 1 cancels, right? And it has to. This is an E field. You're not gonna have an E field, it's a function of eta. Do y'all follow me on this class? So that goes away. Now, let's do the cross on this one, see what happens. I have a minus sign right there, right? I tell people to do this. When you get minus signs, circle them so you don't miss them. As my eyes get, even when my eyes are good, I used to circle because it looks like scratches sometimes in your paper. So negative signs, I like to circle so I don't forget about them. I take a look at this. I have x cross y is z with a minus sign, so I'm going to put simply az down there. And it has a minus sign. I've got that one there. Then I have z cross y, which is minus ax, right? Minus ax. With a minus sign, it's plus. So this stays plus, and this becomes ax. And now, get rid of that. Get rid of that. That is my E field incidence. Y'all follow me? The E field transmitted will have the same exact form. I'm running out of time here, but I want to finish this. Y'all follow me? It's going to have the same form, except now these angles are going to be transmitted angles, and beta here is beta 2. So for the transmitted electric field, now I get minus, I can actually reverse these. Put cosine theta incident AX, minus sine theta transmitted, pardon me. Sine theta transmitted AZ times E naught incident, or E naught transmitted, pardon me, times E to the minus J beta 2 x times the sine of theta transmitted plus z times cosine of theta transmitted. And now I've got the transmitted electric field. I didn't even bother doing the cross product. Finally, I've got to get the actual reflected electric field, right? And again, it would be minus eta times unit vector and direction of propagation crossed into H. Now I come over here, there's one thing I can get from this diagram that saves me some time. You see how both E field in the X direction and in the Z direction is positive? Can you all see that? All right, well that's nice. That means I know the signs of these things are going to be both positive, but I still have to go through the math one time. So this is going to be minus eta 1, unit vector in the direction of propagation is going to be sine of theta incident AX, and it's going to be minus cosine of theta incident AY, or I mean AZ, pardon me, it's going in the negative Z direction. That crossed into the H field. The H field is minus E naught reflected over eta 1 times E to the minus J beta 1, it's x times the sine of theta incident, because the angle of reflection is equal to angle of incidence, and it's going to be minus z times cosine of theta incident, and this is in the AY direction. So here we go for the final one. Remember, I'm just putting things in there based on the definitions over here. Now I turn the crank on that. Everybody see etas cancel? And eta 1 cancels, right? So this goes away, and it's better. Next, I take a look at this, and there's a minus sign that I should have circled. There's a minus sign. I got two minus signs multiplying each other, which will be positive, right? Negative 1 is positive, so gets rid of that. Got rid of that. Now, when I do the math on this, I get x crossed y is z, so I get sine of theta incident az, and then I got z crossed y is minus ax with a minus sign is plus cosine of theta incident or theta reflected, they're the same, ax, then it's times E naught reflected, e to the minus j beta 1 x sine of theta incident minus z cosine of theta incident. And that is my reflected field. Everybody with me? I'm gonna have to stop in a second. All right, I'll just tell you this. Once you have that, the only thing you do is you put the tangent E field on both sides equal to the tangent E field on the other side. Transmitted tangent E field is equal to, and there's only, by the way, which of the components here is the actual one that's parallel to the surface or the tangent field? Has to be the x component, right? Right? Because the x direction is this. So if you take the x component of the E field on one side, it's equal to the x component of the E field on the other. Y'all see that? Because E tan 1 is E tan 2. Z would be perpendicular. So E tan 1 is E tan 2. H tan 1 is H tan 2. The total H field incident is equal, plus the total H field reflected is equal to the total H field transmitted. His transmission and reflection coefficients for these are in your book, but I'm running out of time and I gotta treat that quiz. That's the reason. I will, they're on page 367. We'll talk about Brewster's angle next time, all right? And so we meet on Wednesday. Monday is Memorial Day, right? Let me get to the quiz. What I'd like to do is separate people. So that row, you stay, this row you empty, that row you stay, this row empty, so you move. That row you stay.